Here we're going to continue to look at solving trig equations. And our first example we have is the cosine of x multiplied by the cosine of x plus 1 is equal to 0. So how do we solve this one? Well, at first glance you may think, well, we need to distribute the cosine, but let me give you an example over here. If we had x times x plus 2 equal to 0, or if we had, let's say, x plus 4 times x minus 8 equals to 0. How would we solve these two equations? Well, here, both of these equations are already in factored form. So remember, if we have this equal to 0, then we just simply set each factor equal to 0 and solve for x. So over here, the equation is equal to 0, and we have cosine of x multiplied by cosine of x plus 1. So basically, we have kind of the same thing we have over here, where it's already in factored form. So what we're going to do is simply take each factor, cosine of x, set that equal to 0, and we're going to take the cosine of x plus 1 and set that equal to 0. So now we just simply work with each one separately, just like we did in the previous video. Well, if we look at the cosine of x equals 0, it's already solved. Cosine of x plus 1, we need to move the 1 over. We want to isolate the cosine, so we would have cosine of x equals a negative 1, so we move the 1 to the other side. So here we're looking at where does the cosine of x equal 0 and where does it equal a negative 1. So if we go to our circle, we want to be able to look at where do we have an x value that is either 0 or negative 1. Well, the only place here where we have, if we have a cosine where x is going to be 0, then we know that means we're not going to go left or right. So that would put us up here at the top of the circle at pi over 2. And also, if we were to look at the bottom of the circle, 3 pi over 2. So at this point, we would have our x-coordinate would be 0. And where is the x-coordinate going to be a negative 1? Well, that's going to occur to the left, and that would occur here at pi. So here we're going to have actually three different angles. So if we start with the pi over 2, so we could say that x is going to be equal to pi over 2, and that's because the cosine of pi over 2 would be equal to 0. Then we could add on a multiple of 2 pi. But if you recall from the previous video, if we notice our pi over 2 and 3 pi over 2, they're directly across from each other. So when we go to add on 2 pi, so that we can go ahead and take care of both of these together, we could just add on a multiple of pi. And then we need to look at the other angle, which is x equals pi. And that's the only angle by itself. So there, in order to get back around to this point, we're going to have to add on a multiple of 2 pi. Okay, so if this one, you can really see the difference of what we need to add on. The pi over 2, because we have the other angle of 3 pi over 2, this is only a distance of 1 pi, but to get back around to pi here, we have to add on a multiple of 2 pi. So here we have our answers for this particular equation. All right, the next example, we have 2 sine squared of x minus 1 multiplied by the tangent squared of x minus 3, and all of this is equal to 0. And you probably guessed it here, this is already in our factored form, so once again we can just simply take and set each one of these equations, or each factor rather, and set each factor equal to 0. So then from here we just simply solve each equation separately. So for 2 sine squared x minus 1, we're going to move the 1 over, so we would have 2 sine squared x equals a positive 1, divide by the 2, and we get sine squared x equals 1/2. And to get rid of the square, we're going to take the square root, which means that would be plus or minus. So we would have the sine of x equals plus or minus the square root of 1, which is 1, over the square root of 2. And once again here, we would have to rationalize the denominator, which will make things easier for us. So we would have then the sine of x equals plus or minus the square root of 2 over 2. All right, so let's go ahead and look at the other equation. Again, here we need to solve this, so move the 3 to the other side. We would end up with the tangent squared of x equals positive 3. And then again, to get rid of the square, we would simply take the square root. So we would get then the tangent of x is equal to plus or minus the square root of 3. So now when we look at this, we need to figure out where do we have sine, which is our y-coordinate. Where do we have a y-coordinate of plus or minus square root of 2 over 2? And then we'll come back and we'll look at where do we have our tangent, which is y over x. Where does our y-coordinate over x equal plus or minus the square root of 3? So let's start with our sine function over here. So where do we have a y-coordinate that is, this is our y-coordinate. On the unit circle, where do we have a y-coordinate that is square root of 2 over 2? Okay, well, that's going to be at pi over 4 and 3 pi over 4, 5 pi over 4, and then over here at 7 pi over 4. And once again, we'll notice the ones that have a straight line, pi over 4 to 5 pi over 4. Here we have a straight line across from each other. So that means we could simply say then x is equal to pi over 4 plus our multiple of pi. And then we could do the same thing with 3 pi over 4 and 7 pi over 4. They're straight across from each other. So therefore we would have x equals 3 pi over 4 plus a multiple of 1 pi. Okay, so there's the answers for this part of the equation. And then we still have more answers looking at the tangent. So if we look at the tangent now, we're looking for where do we have our y-coordinate over the x-coordinate to equal the square root of 3 over, plus or minus the square root of 3. Where does y over x equal plus or minus the square root of 3? Well, if we look at the circle, that's going to happen here at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So just like we did before here, the pi over 3 and 4 pi over 3 are straight across from each other, so we could write this as x equals pi over 3, and then add on a multiple of pi. And then if we look at 2 pi over 3 and 5 pi over 3, they're straight across from each other as well, so we could take x equals 2 pi over 3, and once again simply add on a multiple of pi. So there's all of the answers that would solve this particular equation. So any of these values of x we could plug back in here to the original equation, and it would be equal to 0. All right, one more example. And this one you will want to make note of. This one's going to be a little bit different yet. We have the sine squared of x equals 3 cosine squared x. Now this one you'll notice is different from all the other equations we've solved so far, in that here we actually have two different trig functions. And well, let me go back. This actually, the previous one here, we actually noticed we had two different functions. We had a sine function and a tangent function. Now we could deal with these two because they were being multiplied together, so we could separate them by setting each factor equal to 0. So that's how this next one is different. We'll notice here we're not looking at factors. We have a sine function on one side and the cosine on the other. So somehow we need to, if possible, change our sine function to cosine or change the cosine function to sine. Now we have sine squared x. Can you think of any way that we could take our sine squared x and change that to a cosine? Well, if we think of our Pythagorean identity, we have sine squared x plus cosine squared x is equal to 1. If we solve this for the sine squared x, we would subtract cosine, so that would be 1 minus cosine squared x. So sine squared is equal to 1 minus cosine squared. So up here we can replace this or substitute this with 1 minus the cosine square of x. And then that would be equal to our 3 cosine squared x. So now we have one trig function. So now we need to isolate our cosine function. And here we want to, we have a negative cosine squared and a 3 cosine squared. For example, what if you had this equation here? What if you had 1 minus x equals 3x? What would you do to get the variable on one side? Well, hopefully you'd say, well, I need to add x to both sides, and we would get 1 equals 4x. So over here, we're going to do exactly the same thing. We're going to add cosine squared x, and that's 1 cosine squared x. So over here, it's going to cancel out, and we're left with 1 equals, over here, 3 cosine squared plus cosine squared. And again, because these have the same exponent, we can add those together, and we would get 4 cosine squared x. So by doing this now, we simply can solve for our cosine function just like before. So we need to get the cosine squared by itself. So to get rid of the 4, we could divide that away. Cosine squared x then would be equal to 1 over 4. And I'm going to switch the sides here. I'm going to rewrite this. I think it's easier for you to see if I switch this to cosine squared equals 1/4. And again, you don't have to do that. And now we want to get rid of the square, so we would take the square root of both sides, which means that we have to put in plus or minus. So therefore, the cosine of x is equal to plus or minus the square root of 1, which is 1, and the square root of 4, which would be equal to 2. So then we just have to go to our unit circle once again and look at where do we have an x value of either positive or negative 1/2. So if we go to our circle, then we're going to notice that if we look in the first quadrant, that's going to occur at pi over 3, and then again over here at 2 pi over 3, 4 pi over 3, and 5 pi over 3. So that means we would have x equals pi over 3. And again, because this is going straight across to 4 pi over 3, we can simply add on one multiple, or a multiple of 1 pi rather. And then for 2 pi over 3 and 5 pi over 3, we could simply say x is equal to 2 pi over 3 and add on a multiple of pi. Okay, so with this problem, we're looking at if you have two different trig functions, usually is there a way that we can rewrite it in terms of one trig function? Like example number 2 here though, notice because it's being multiplied, and we can simply set them equal to each other, there's no need to make the sine function tangent or try to make the tangent function sine. So as long as they're separated here with multiplication, then we could simply set each factor equal to 0. But if we have something here where it's on different sides of the equation, or if something's being added or subtracted, then we usually look at a trig identity to condense it to one type of trig function.